All right, great. Continue. All right. So, and let me see. Let me just also see my own. Let's do video here. And okay, guys, welcome. Today I'm trying a slightly different setup. I'm calling from my iPad. Just hopefully it won't be as and I have my laptop available open as well. So I might share some things from there, but hopefully it won't be as glitchy as last time. Make this smaller and make this okay. I need to look at this. All right. So just a few comments. First, can you guys, let me just pull up the participants. Sorry. Okay. See everyone here and chat. Excellent. And then I'm going to hide this one. Okay, excellent. So just a few comments, so maybe let a few more people enter. So I returned all the exams. About half of the people, half of students didn't pass, scores ranging from like 0 to 6. So if you're one of those students, don't be too concerned. Believe it or not, I'm actually very happy about that because you know, that means that you were honest. B, you tried. I saw a lot of people actually try, like get a few problems correct. And C is I know that you guys can, those students who didn't pass, who got a 0, like I know for sure you can you know, get a good grade on the test, if not ace it even. So I had some office hours just before this class. I'll be available after class if any of you have extra questions about the test you want to go over. And then potentially on Monday at 1 p.m. I can also do something if you guys are available then, or just email me if you can't make any of those times. Your schedule. I know some of you are back to like sports and stuff. Just email me so that we can schedule something to talk. And yeah, one thing, if you're falling behind, I recommend like watching the videos starting with lecture 11. And you know, when you're watching videos, I mentioned before, watch. It helps me to watch it through and fast forwarding like a double speed, and then slowing it down when I'm a little bit confused, and then watching it multiple times until the idea clicks, or just taking notes. And you can send me an email about something if it, or ask me in office hours. But yeah, I would like, before any student that failed and wants to do a retake, I want to see you write up a practice exam correctly, with explanation of kind of what your ideas are for each question, and also maybe what you learned and how you prepared differently this time around. And then I'll let you take a retake and we'll count that score instead. Okay, does that sound reasonable? And can you guys hear me okay? Okay, great, awesome. So today we're going to move forward with bell curves and z-scores. And I'll mention this thing again at the end of the class. So bell curves and z-scores. So last class, we talked about a very special bell curve called the standard normal distribution. And the way I think of the standard bell curve is, or the standard normal distribution, it's kind of like the basic parabola, right? It's like y equals x squared. And we know all the points on y equals x squared. And if you needed to graph any other parabola, you could kind of get it from that basic parabola. So in my mind, I think of this as kind of the most useful bell curve. And any information that we need to get out of another bell curve is actually kind of part of it can be figured out from the standard normal bell curve. So the standard normal distribution and we use a capital letter because it's a random variable, the script z, and we write that it's distributed. This little squiggly sign means like it's a distribution that follows the normal distribution with parameter 0 as its mean and 1 as its standard deviation. And all that means is it's centered at the outcome 0, so it's centered along the y-axis essentially, and it's spread out where most of the data falls between -1 and 1. Most of the area is between -1 and 1. Move this over here a little bit. Okay, so one thing that we're interested in, because we're talking about probabilities, is we want to figure out the area under the curve. So we have something called a z-score table, and I'll share that with you guys in a minute, and we're going to use that extensively. So today's lesson is really about learning. It's a really important lesson about learning how to use this table. There's a z-score table that tells probabilities under the standard normal bell curve. So for example, I'm going to draw the bell curve right here. Here's the standard normal bell curve. So a little shape here, here's 0. One thing I might ask is, what is the probability, and this is how we kind of word these questions, that the outcome z is less than 0.75. So what's the chance that when you observe, you pick something from the bell curve, or pick something from the real numbers from -∞, you just think of a number, but your numbers are distributed, your random numbers are distributed according to the standard normal bell curve. What's the chance that you'll just randomly think of a number that's less than 0.75? Well, the answer to that question is you have to use the area under the distribution. So here's 0.75, and we know the way that the bell curve is defined, that the entire area, the entire thing that goes on forever, let me just write it out, draw it out here. The entire area is 100%, or is just the number 1. But what we want to figure out is, what is the area up to this red line? And that would give us, that's the interpretation of the statement. What is the probability that z, the z outcome that you get, is going to be less than 0.75? Okay. And these are the types of questions that you can answer using the z-score table. But first, any questions at all about, and don't be shy, about this sort of initial setup? By the way, just to do a sanity check, what do you guys think is the probability, before we get into the table, just do some sort of um, uh, question so make sure we're all on the same page. What would be the probability that somebody guesses an outcome according to the standard normal distribution, that they guess a number, and that what's the chance that the number is less than 0? What do you guys think?
50%.
Nice. Who was that, Dimitri? Who was it?
That was Andrew.
Oh, Andrew. Yeah, Andrew. Do you want to explain why it's 50%?
Because if all the data falls between 1 and 0, 1 and -1, 0 is the halfway point.
Oh, good. Okay, good comment. So, all the data actually most of the data falls between -1 and 1. Most of the, but it actually goes all the way to negative infinity and infinity.
Okay, but the bell curve is also mirrored on the origin.
That's right. Exactly, it's mirrored on the origin. So whatever is below 0 is also the same part as whatever is above 0. Exactly. So it's got to be 50%. Awesome. Nice, Archer. Very good. Excellent. Andrew, very good. Also, that's awesome. Okay, so we're going to use that mirroring trick. You can apply that mirroring trick. We're not going to necessarily have to use it, but keeping that in mind is really nice. Okay, I'm going to share with you guys a table so that we can. The thing about this standard bell curve, it's a very difficult function to actually like calculate by hand. You guys saw it comes from e to the negative x squared, and e is like pi. So forget about it. It's like a really difficult thing you can't do it by hand really. So we use a computer, and we have a table that basically for different I wonder if there's a way I can, for different thresholds, it gives us the area under the curve, and that's called the z-score table. So let me just pull that up and share that with you guys. And also please bookmark this link or just save the PDF, because you're gonna use it for homework and for a lot of things. Yeah, this is okay. All right. Yeah, just ztable.com. Oh, hang on, send to everyone. Okay, so please pull that up, and I will also let me see here. I will share my screen just to show you how it works. So let me share the screen. Okay. So the way this table works is a little bit confusing at first, and please ask me any question about this table. The way it works is the z values are expressed over here. You start off with the kind of a really low z value, and it goes up all the way. There's 2 pages. It goes to positive z values. So that's the first column. It tells you the z values. The numbers inside of the table are probabilities. They represent the gray area. They represent how much area is in the shaded region. And the way the z table works is it's always the area. It always gives you the area to the left of your z value. And now, just kind of so that we have more precision. Oh no. No. I don't know what's going on here. Oh, okay, cool. Okay, so that we have more precision, these values on the top row, those allow us to get a little bit more refined with the z kind of different z scores or z values. So let me just show you kind of how to do points, how to find the area to the left of 0.75. So 0.75 is not here, right? We only have 0.6, 0.7. But if we want 0.75, you start off with 0.7, and then you look on the top row. You say, oh, you want to add 0.05. So it's going to be this row, and this column the 0.05 column would represent 0.75. And you just have to look for that number that's in that row and column, and it's 0.7734. And look at this. As we go to 0.76, which would be the next spot over, it just goes up slightly. And that makes sense, right? Because I think of the Z line as kind of like a sweeper. And as you move over just a little bit to the right, you're capturing a little bit more area. So if you look at this table, each time you go over to the right a little bit, the numbers get a little bit bigger. And then at 0.78, 0.79, it gets a little bit bigger. And then you're going to jump to the next row, 0.80. So it's a little bit of a weird way to present a table of data or like a function. But it's nice because like each row represents the 10th place and each column represents the 100th place. And you got to figure out the right spot that's referring to the number that you are interested in, referring to the threshold value. Okay. So that's the chance. There's a 77% chance that if you're picking from the real number line, according to the standard normal distribution, there's a 77% chance or the chance that your number is less than 0.75 is going to be 77.34%. And take a look at zero. The chance that you pick something less than 0 is going to be 0.00. That's 50% right there. Okay. Any questions? How do you guys feel about this? And it took me a while to also get this. I remember I was a little confused, always a little confused with this table. So I'm going to go back to the whiteboard here. Oops. And I'm going to do, and by the way, does everyone have the table up?
Would you want us to write it down? Or?
Yeah, I'm going to show you how to write it down.
Okay.
Okay, Angel, very good question. So when it says the chance of Z being 0, that's, why is it 50%? So if Z is 0, right, because it's a standard normal, that's telling us that 0 is right at the middle of the whole like distribution. And because it was e to the negative x squared, we know that it's symmetric. So that tells us that the area, which we know is 100% by design, is going to be half and half right at the number 0. So that's why it's 50%. And look at this. The more negative you are, like the smaller this gray area gets. When you're talking about a z-score of negative 3.4, the chance of being like below that is really, really low. Like that's, what is that? That's less than 0.03%. Because it's 0.0 is 3/10,000ths. Okay, hang on. I have some good questions here. 1 second. Sorry, guys. If you were to switch the probability sign to be greater, Archer, very good. If you wanted to do greater, that's the thing about this table is we'll see you can use the area to the left to answer basically any type of question about this distribution. So for example, Archer says, if you wanted it to be greater than 0.75, well, because we know the entire bell curve is the number 1, the area is going to be 1 or 100%. If you want to know the area to the right, you just subtract the area to the left. So that's exactly a good comment. That's very good. Let me go back to my screen here. Oh, I see. Unfortunately, it erases. Let me see something also here. more meeting settings, general. I want to allow more people to share so it doesn't stop my sharing, but okay, whatever, that's fine. So what we just saw is that the probability of Z being less than 0.75 is equal to 0.7743. And actually, once you get the hang of this table, it's pretty fun. It's really what is it? 3-4. Thank you. Okay. And let's see here. Let's do another one. With which other one did I ask in the notes? Let's do kind of what Archer suggested here. Let's try another one. What about the probability of Z being greater than 1.5? And one really important thing in these questions is that you're very, and I'm going to be really a stickler for these, is that you're very careful about talking about the event, which is like the outcome, the Z value, and the probability. So don't confuse this number, which is kind of what the Z value is, even though it's very close to this. They have nothing to do with each other, right? This is just where the Z value happens to be, and this is an area. This is a probability. So that's we're going to be really careful with the way we write things and talk about them. And you'll see because there's not really much going on here. I do want you to be proper with the way you use the terminology and notation. Okay, so can you guys message me what probability you got for that? And let me know if you're totally stuck, you're not sure at all how to do it. Nice, getting some good answers, good. Okay, cool. All right, very good. Nice, a few students are confused, good. And a few students got it, awesome. Angel, do you want to explain kind of what your thought process was?
What I did was find the probability of 1.5 and then take that away from 1.
Excellent. So I'm going to draw it out and then we're going to do it in the table, okay? So what this means is we have our bell curve. Here's 1.5. And we're going to use the table. What Angel did was he used the table to figure out this area. So whatever you figure out there, you can find this from the table. And then once you find that number, you can do 1 minus that number to get the remaining part, which is this is what we want. So this is the answer. This is the answer. So I'm going to write it as an equation here. This is equal to 100% minus the probability that the Z value is less than 1.5. And in particular, it's 1.50, right? Okay. So those students who are a little bit lost, are you okay with what I wrote on the whiteboard so far? Now we're gonna jump to the table to figure out the red area. But does the setup make sense? Or any questions about what I'm drawing here, why I'm drawing it?
Are we looking for like I guess I don't know, sorry, I'm trying to think about how to word this. Are we trying to find the probability of values over 1.5?
Okay, so this is an important question. The way that we talk about continuous random variable or continuous distribution is like for example, if I told you, hey, pick any number from -infinity to infinity, it's kind of hard to say what's the chance of getting some specific number, right? So what we do in math and statistics and probability is we have this thing, we have the continuous distribution, continuous probability distribution. And the way you can interpret that is like, it's like an infinite, infinitely like continuous histogram. So the points where it's higher, the parts where it's higher, that gives you regions where you're more likely to pick the numbers along the x-axis. So we create a curve called the standard normal bell curve, and the entire area is 1 under the curve. And that represents that the chance of picking any given number is 1, like it's 100%. And then we can say the chance of picking like some, maybe I'll write it like this. So if you have your bell curve, and it doesn't have to be a bell curve, but this is general, like for any continuous distribution. And again, think of it like kind of like a histogram, you know, like a histogram is like, has a bunch of bars, right? This is like a continuous version of a histogram. You know, when you say, what's the chance of getting a certain range in a histogram, you just have to add up the probabilities of the bars, like the heights of the bars. So it's analogous to that, where if I give you some continuous distribution and I say, what's the chance of going like in this interval from A to B? So what's the probability that X, which is the outcome, is greater than A but less than B? Well, what we say is we define that to be the area under the curve. It's the area of the curve. Kai, does that help a little bit?
Yeah, I think.
It's a little bit weird, right? Like, because I'm not saying like I'm not giving like ranges, like, you know, like a histogram, right? People say how are the scores of the students distributed? Like how many students got a score between 700 and 710, 710, 720, and there's different percents that you can make. So this is like a version of that, but it's a continuous version of that.
Okay.
And instead of adding up the bars in the histogram, we talk about area.
Okay, that makes sense. Thank you.
And in particular, this table is a very special table. The table that we have access to, because it's difficult. Like, we're not calculators. We can't just look at the picture and know how much area is in there. We need to kind of have it. We need to basically have it summarized. A computer calculates all the areas and summarizes it in the table so that we can access it later. So this table is very special. The table, the z-score table, it gives us all the areas. Whoops, that's not what I wanted to do. It gives us the areas that are to the left of a specific threshold. So you can look up a threshold A, and you get the chance of picking a number, or X value, that's less than A. So for example, one probability that you can find in the table would be this green area. So let's go back to this one, and let's think about this. The chance, and I used X previously because just to say it's any random variable that has a continuous like bell curve, or doesn't even have to be a bell curve. It could just be any sort of continuous distribution above the x-axis is going to be give you some probability distribution. But in particular, when we use the standard normal bell curve, we use the letter Z. That's our outcome. So the chance of observing Z greater than 1.5, the table doesn't give me that directly. Instead, I have to find the area to the left of 1.5 and subtract that from the number 1, which represents 100%. So let's go to the table and try to find where 1.5 is. So I'm gonna just do this. Here, I'm gonna share this screen now. Actually, hang on. let me go see if I can. It's annoying because I lose my I lose the chat, but okay, I'm just gonna do Chrome. So now I'm going to look for 1.5 here, and 1.5 is right here. And in particular, I want 1.50 because it's exactly 1.5. I didn't ask 1.51, 1.52. I said 1.50. So the probability of observing something to the left of 1.5 is about 93.32%. Okay. So therefore, that's going to leave me with roughly 6.8% that's going to be to the right. Or was it 6.6 something? Yeah, 6.68% to the right. Any questions on how I got this number 0.9332? And let me know, is it those students who were a little bit confused before, do you feel a little bit better now, or still any questions? So now I'm gonna, let me see if I can do a new share right here, or if it still gives me some problems. Actually, let me stop. So let me go to the whiteboard. So therefore, probability of z being greater than 1.5 is equal to probability is equal to, sorry, 1 minus probability z less than 1.5, and this is equal to 1 minus and I got to find that number there. We just found that number in the table. That was 0.933. Thank you, 0.9332, and so this is going to be 0.0. Thanks guys. Awesome, appreciate that. 0.0668, which is roughly 6.7%. Okay. Any questions on the picture and the table, how I kind of came up with this answer? And thumbs up if you're good with it, and let me know, definitely let me know here if you have any questions. Just to make sure that everyone's on the same page. And we'll do a bunch more practice of this as well. All right, let's go to the next idea, where we're going to try to find the probability of interval. So now not just going to the left and going to the right, but in an actual interval. By the way, before we move on, does anyone see a shortcut? Rather than doing subtraction, there's actually a shortcut you can do to find the probability of greater than. And I'm not going to expect you to do it, but if you want to, you're welcome to. Nice. Yes, Ace, what do you suggest there? I like that idea.
Well, there are two tables, and one has the positive values, but the other has negative values. And if you just do negative 0.5 on the first table, then you get the same answer.
Exactly. Because it's symmetric, when you want to answer the greater than question, like greater than 1.5, that's the equivalent to the area that's to the left of negative 1.5. So you can do it in one step if you just look up negative 1.5 in the table. And I'm just going to give you guys a minute. Please check that out, making sure that when you look up negative 1.5, you actually get the answer that we needed right away. So here's negative 1.5. And if this is going to be available in the table and that's going to be the same. These are the same. So that's a neat thing you can do. You don't have to do it if it you know, it's a little bit confusing sometimes, but it's nice to see that as an option as well. Excellent. And keep in mind, we're being really, really careful about how we write these things. So I'm going to be a stickler that you write this. What's inside here is the range of outcomes that you're interested in. But once you find the probability, it's just going to be a percentage, and there's no more p of something like that or whatever. So this is a percentage between 0 and 1. So the outcomes can be any real number. Like this can be, you can compare z to like -infinity or 500, whatever. But these numbers are always going to be between 0 and 1. Okay, let's do an important concept now, which I think you will have the tools to do it, but I'll walk you through it. Let's try to figure out the probability of an interval. So, so this is going to be the probability of being between -0.32 and this is the z value, the outcome. So what's the chance that you just randomly, according to the standard normal bell curve, that you pick a number randomly between -0.32 and 1.15? So what are the chances that your outcomes range between there? Well, we don't have access to that kind of information in the table, but we can figure it out because we can take care of areas. We can work with different areas to figure that out. So I'm going to draw the bell curve here. So and by the way, I always draw the bell curve because it just makes sure that I have a sanity check. If you saw in the previous question, if you look at that that little green area, this is, by the way, we call this a tail. We call this a little tail because you see it looks like a little tail. That's all. So you see the tail has a really small percentage, and the middle part is kind of like a body. Okay, nice. I see somebody wrote a good. I think Angel wrote a good. Wait, why didn't I see it in the chat? Hang on. Oh, okay, Angel, you wrote private. Very good. Yeah. So so here's 1.15. I'm going to draw it first, and here's -0.32, and here's 0 in the middle. But you don't actually need to draw 0. Don't worry about it. I'm going to get rid of it, but whatever. And we want to figure out the region, the area underneath both of them. So that's going to be, nope. That's going to be in between them. So we want to know this yellow area. Okay. And I don't have that in the table, but can anyone see a strategy that I can use with the table to figure out that yellow area? It's kind of like a little puzzle. Angel, you want to explain what your idea is?
Take the probability of z being less than 1.15 and then subtracting it by the probability of z being less than -0.32.
Awesome. I love how you said it. That's perfect. So if you look at it from the picture, what Angel suggested first, I'm going to draw the picture first, is he said, okay, fine. We have the table. The table gives us always to the left of a threshold of a z value. So let's figure out first the area to the left of 1.15. That's going to be this whole thing right here. It goes on forever, right? That the table gives us. But that's too much. That's got that extra tail that we don't need. So then just take away the, let me do it in red, take away this green tail, this red tail right here. Okay? And that's going to give us the answer. And I'm going to write it in a note form. This is equal to probability z less than 1.15. That's the blue region outlined. minus the red region, which is going to be probability of z being less than negative 0.32. That's the red region. And that should just overall equal whatever's left over. That should be the middle part that we want, which is the yellow region. Don't try to memorize the formula, like the pattern of the formula, like what's less than that. Actually understand how to talk about this, and then you'll see how easy it is. It's to get to use the table to figure out a segment, the probability of an interval. Just take the entire thing to the left and subtract the left tail. That's all it's saying. Okay, how about you guys try to do this? I'm going to do it on my chart. I don't want to share the screen because I'm going to lose everything that I drew here. But can you guys look up each probability and chat me what numbers you get, and then we'll subtract them. Okay, and making sure that you can do it. Okay, so and don't be shy if you can't find the probability. If you can't find, so you're going to have to look up two different things in the table. You're going to have to look up 1.15 and negative 0.32 in the table, and then write those down and then subtract them in the calculator. But make sure you can find them. Let me know if you can't find them, okay? So I'm going to look it up here in the table. So let's see, 1.15. So I go to 1.1 first, and then I see I go to the 0.05 column. So 1.1, I got this number. Nice, Archer, I see you got it, 0.8749. So I'm going to write it, this is equal to 0.8749, I believe. And then 1.15, good. And then I got to go to negative 0.32. So that's going to be the first page. I see negative 0.3, but I want negative 0.32. So I got to go another column down, another column in. That's 0.3745 minus 0.3745. And now I just subtract those numbers. Those are different areas. I can subtract the areas to get what's left over. And that came out to what? About 50. Oh, perfect. 50. This is 0.5004, which is 50.04%. All right. Any questions about finding those two numbers? Please give me a thumbs up if you got it, and ask any question if you did not find those numbers, the 0.8749 and the 0.3745. I'm happy to kind of go into the chart and show you guys. Oh, let me see. Maybe I can. Oh, I know what I can do. Hang on. Wait a second. I know what I can do. My video is on, right? So, yeah. Okay. Any questions? Are you guys comfortable with the chart? Good. Don't hesitate to ask about this. All right, let's go to the next idea. So there's an interpretation here. The chance of picking from a bell curve that is between an outcome that's going to be between -0.32 and 1.15, negative 0.32 and 1.15 standard deviations away from average is about 50%. Because it's a standard bell curve. All right, now we're going to do something where we go backwards, and we're going to find something called the percentile. Does anyone, have you guys heard of, just show of hands, have you heard of percentiles? Where have you guys seen percentiles? Anyone want to speak up and share where they've heard of it? Where is it really commonly? Oh, Olivia, that's a good one. You want to explain that one a little bit?
Yeah, I said I see percentiles at the doctor because like when you get your form after you have your like your physical and stuff, it's like, oh, I mean, like I'm in the 3rd percentile for height, like just stuff like that.
Okay, let's go with that. If you're in the 3rd percentile for height, what does that mean? Are you really tall or really short?
I am very short.
Oh, okay, okay. So third percentile means that. How would you interpret what that means?
Well, it just like I kind of like, I guess you could say it's like where you stand and like maybe like for my age, like in my height, I'm in the third percentile. So I guess it's kind of like not. I guess I mean, it's kind of hard to explain. It's not average, but I think it's kind of average, I guess.
Okay, you're very close. It's definitely about like you're comparing you to people that are similar like age as you, like similar age for sure. It just means the third percentile means that if you take all people, you are roughly taller than 3% of people.
So it refers to where you are in the standard deviation of things then.
It's related to standard deviation, but it doesn't have to be. It could be. It's related to bell curves usually, but it doesn't actually have to be. It just means like in the population, if you're in a certain percentile, then that number, that percentile tells you how many people are below you, what percent are below you, and the other percent is going to be above, above your score. So, for example, my daughter is in the 40th percentile. Like we were worried that she's a little bit like wasn't eating that much, but she's in the 40th or 35th percentile of like baby weight. So she's only, she's bigger than 35% of babies, but she's, that's why she's a little bit smaller, below average. If somebody's IQ is in the 99th percentile, then they are smarter than 99% of people, or their IQ score is higher than 99% of people. So the percentiles are very good. Like when you take a standardized test, I see, BMI stuff also. So doctor stuff for sure, they like to put you in percentiles. And lower high percentile isn't bad or anything. Just it's important so that you can compare your intake and your exercise and your routines, like relative to. It should be not just. It's not this. There's not a one size fits all solution like for healthcare. It all depends on what percentile you're in, and a lot of different factors can determine like what's the optimal, diet, nutrition, exercise, all that stuff. Yeah, it's also used a lot for test scores. So when you take a test, you want to get into the highest percentiles possible. That means you did better than as many people as you could. So if you look at what we're actually doing here is what the numbers are that are inside the z-score table, they're actually percentiles for this distribution. That's the numbers that are inside the middle of the table, those probabilities. For example, if you pick the number in the standard normal distribution, if you pick the number 1.15, that number is going to be in the 87th or 88th, rough 87.49 percentile. Because it's higher than 87% of other numbers, or it's 87% of other outcomes. So that's how we think about percentiles, and that's the connection with this table. So let me kind of expand on that a little bit. So to find a percentile, or to find the threshold for a percentile, to find a threshold, for percentile, we're going to work backwards. We're given a probability or a desired percentile that we want to achieve. Probability. And then we get the threshold. So here's a nice question you might find. For the standard bell curve, what is the threshold, or what is the cutoff? Threshold is kind of just means like cutoff score, right? So what is the threshold value for the 95th percentile? And this is an important type of question. Like you might, the reason you might ask this is might say, okay, I'm only going to give the top 5% an A or something like that, or only going to accept the top 5% into the program. So I need to know where the cutoff is for this percentile. Okay, so what that's asking is a bit different from what we saw before. We want to figure out the Z value this time, and we're given the area under the curve. So we know that this is 0.95 now, but we want to figure out what is this missing Z value? What is this? So I'm going to go into the table, and now I'm no longer looking like trying to narrow it down and find I'm not looking up the Z value and like zeroing in on the probability. I'm going backwards. So I'm looking inside the table for the number point, because it's 95%. So I'm looking for the number that's 0.95. And you might not, as Archer says, you might not find it exactly there. So if you look in the table, like in all the numbers, if you notice, they all range from 0 to 1, right? So look at 0.95. I can't find it exactly, but I'm looking there really closely. I see a bunch of 0.95s. I see two numbers that are really close. I see, do you guys see them? And let me know if you don't. Do you guys see where 0.9495 and 0.9505 are? Nice. I see a few students found them. So we're going to go backwards and we're going to find the Z-score that's roughly there. And you can, this is an estimate because this is a table. This is not a computer. It's a summary of data. So we're not going to get exactly right. So you can either use 1.64 or 1.65. Pick whichever one is closer to your percentile. And in this case, they're the same distance away, I think, right? Let me see, 0.94. Are they the same? 0.9. Yeah, they are. They're 0.9495 and 0.9505. I'm seeing those two numbers. Those are equally distant from 0.95. So pick 1.65. So this, looking in the table, I'm going to pick Z equals about 1.65. Okay. Any questions on how I got that number 1.65 as the threshold value? Awesome. Very good, Archer. Anyone else? Anyone have any questions about it? Nice, Brandon. Awesome. Oh, Angel, what do you mean by your question? Angel, I didn't follow. What do you mean? What do you mean? Why isn't it something worth 0.05?
So what the percentile is basically try to find the value of something up to that point.
Yeah. So the percentile is the percentile is the threshold value, I guess, that would give you the desired percent up to that point. Exactly. I see. Why, if it's in the middle, why wouldn't it be about one? You're totally right. Is that what you meant? What Archer is suggesting, like to do 1.645? That's a really good estimate for the exact number. Yeah. Is that what you were suggesting? Okay, so let's see here. I want to do a little bit more. All right. So yeah, there's a little bit more I want to go through, maybe like 20 minutes. So any questions so far about the standard normal bell curve? So the next idea is really important. And we're going to keep using the standard normal bell curve. So you have to be really comfortable with that. But the next idea is what happens if we're not working with the standard bell curve? So what happens if mu is not equal to 0, if you have a bell curve that's not the middle value is 0, and the standard deviation is not equal to 1? So let's say we have, here's an example of different situations. Let's say we're talking about the weight of an elephant, the random weight of an elephant. Just pick an elephant at random. And if we know that it's distributed according to a bell curve, we can say that, oh, the bell curve has the mean, the middle of the bell curve, most elephants are around 13,000 pounds. And then the standard deviation, which is kind of like the range plus or minus where you would expect about 96% of elephants to fall into, is about 2,000 pounds. So this could also be a bell curve, but it's no longer the standard bell curve. Another example might be in completely different types of numbers. If you're manufacturing something at Tesla, you're in charge of making sure that the doors close at a certain precision, like there's no gap. I don't know if you guys follow the drama about Tesla. Sometimes they talk about they used to complain that when you close the doors, the gap between the door frame and the door would be too big. So maybe at Tesla, there's somebody with a ruler measuring that, and they say, well, we want the average gap to be about half a centimeter. So at Tesla, you can have something happening with a bell curve distribution where the average is about half a centimeter. So that'll be the middle of the bell curve, and give or take about a tenth of a centimeter. So obviously, when you manufacture something, you get all the devices that we have, like Macs, phones, smartphones. They are made by machines and pretty much the same every time, but there's a tiny bit of variation each time. It's not like to the atom. It's not perfect to the atom, right? Maybe there's a few millimeters of difference here and there. So this is probably actually, if you're talking about manufacturing, a tenth of a centimeter. I don't know if you've ever built something and you're off by a tenth of a centimeter. That's not bad. So unless you're talking about a microscope or something, then it could be not good. So how do we answer questions that might be related to bell curves that no longer have around 0 and 1? What we can do is we essentially transform our question into a question about a standard normal bell curve. And the main idea is that instead of talking about distance from the mean, we just divide the distance from the mean, we divide it by the standard deviation. And what that does is it turns everything into the standard normal bell curve. Because recall, if we just talk about standard deviations, in the standard normal bell curve, the number 1 represented one standard deviation because the size of a standard deviation was just 1. So let me do an example so that hopefully it'll become clear. So sticking with the example of the elephant, we have mu. So if elephant weight is distributed normally, the normal distribution, normal distribution. So the bell curve has a bell curve shape. So this is an assumption. And the bell curve has mu. The average weight of the elephants is going to be 13,000. And the standard deviation is 2,000. Oh yes, yeah, Kai, I'll go back for just a sec here. Oh, okay. Yeah, just let me know when you finish. Okay, sweet. So we're just copying this situation with the elephant. We want to understand what's the chance of observing an elephant. So I'm going to use lowercase e for the weight of the elephant. That's between 10,000 pounds and 13,500 pounds. Well, I don't have a table for that. You know, if I had a calculator, maybe I could do it with a calculator. So I don't have a table for that. But what I can do is I can transform these numbers. I can change these numbers into z-scores, into z-values. And essentially what I'm doing when I do that is I just compare how far away these are to the mean, and I divide by the standard deviation. So I'm just expressing everything in terms of a standard deviation. So can you guys just kind of, without looking at it, if the mean is 13,000 and the standard deviation is 2,000, how many standard deviations is 13,500 away from 13,000? What do you guys think? I'm not going to give you a formula just yet. I just want you to think about it a little bit. How many standard deviations away is 13,500 from 13,000? Does anyone see it? Angel, very good. It's a little bit off. Angel, what's your reasoning? How do you get that?
The offset between 13,500 and 13,000, which is the mean, is, well, 500. And since we're supposed to divide it by the standard deviation, it would be 500 over 2,000.
Exactly. And it comes out to just 1/4, right? If you're a standard deviation above 13,000, that's going to be a full 2,000. That would be if you're at 15,000. That would be one standard deviation away. But this is not that far away. It's only 500 units away. And similarly, 10,000, how many standard deviations away is 10,000? Is that below or above? What do you guys think about that one? Well, for 10,000, is it below or above average? It's 3,000 away, but it's below because it's below average. So Angel, exactly, it's negative 3,000 over 2,000 is 1.5. So it's negative 1.5 standard deviations away from the origin. So when it's below average, we say it's a negative number of standard deviations. And when it's above average, we say it's a positive number of standard deviations. And the number of standard deviations, there's a formula for that, and we call that the z-value, which relates to the standard normal curve. And we say this is the formula. The z-score, the z-value, is equal to the actual outcome that you're talking about minus the mean over divided by the standard deviation. And it's a really simple concept. It's just a transformation. It allows you to compare things, how far away things are and how rare things are that are like at a completely different scales. So you can understand if an elephant is one standard deviation like above average height, above average weight, you know, that's a pretty heavy elephant. That's unusual to see that. Just like you can say, oh, hey, you know, if you're a Tesla mechanic and you say, oh no, I observed a door that has a gap of like more than one standard deviation away from average, that's also just as unusual as observing that elephant that's you know, over 15,000 pounds. That's the idea. It allows us this discussion of standard deviation allows us to compare probabilities or talk about probabilities with events that are kind of, you know, have different means and different standard deviations. And that's why we call it the standard normal bell curve, because everything is essentially using that. So now I'm going to calculate Z1, which will be the first value. That was what Angel found here, 13,500 over 13,000 over 2,000. And this is just equal to 0.25. And then I find Z2, which is going to be the second Z value, which is 10,000 is 10,000 minus 13,000 all over 2,000, which is negative 1.5. So that's it. Z-score is just the number of standard deviations away you are from the mean. And so what that allows me to do is now I can answer this question using the Z table. I convert this no longer using E, but now I'm talking about the Z value. Now I want to know what's the chance that the Z value is greater than negative 1.5, but less than 0.25. And that is what we did before. We saw how to answer that. That's the question of finding the area on the standard normal bell curve, the Z-score table, that's between two values. And so we saw how to do that earlier. Any questions on how I got to this point? Okay, please try to find these numbers. Use the Z-score table to find these two values. And remember how to set this up. Oh, hang on. This good question. The answer here will be a probability. So remember, this is going to be equal to the probability of Z being less than 0.25 minus the probability of Z being less than negative 1.5. Let me draw another picture here. So this is what we're asking. We have a bell curve. This is the bell curve for the elephants. 13,000. This is 13,000. Let me do it actually a little bit closer. This is 13,500 right here. And then this one would be 10,000. So what we originally wanted to answer was what's the area of the yellow region in between these 10,000 and 13,500. But this is, I don't have the table for this, so I can't do it without a calculator or without a computer. However, I can transform it to a question that I do know how to answer. So this is for E. This is E, but I can transform it to a Z table or Z distribution or standard normal distribution, where instead it's just going to be here's 0, here's 0.25, and here's negative 1.5. And now I just want to figure out the area in between 1.5 and 0.25. And that's that formula that we did earlier. So I'm just going to pull this back up here so you guys can finish writing. All right. And then, yeah, you can find two numbers there. And I'm just going to write down what the numbers are here. And stop me if you didn't find them. Let me see. By the way, when you chat, can you message the other Daniel Minsky? The one that's not the host. because especially if you chat privately, because I don't see it. It's harder for me to reply on my iPad. Nice, excellent. I see Ace. Good job. So if you use the table to look up these numbers, and it's a good practice, please do it. Don't just listen to me doing it. If you're not practicing as we're doing it, it's really not good, because like it's one thing to watch me do it and say, oh, this is what I got from the table. And it's another thing to actually look it up yourself. Because I've been there where I kind of just like said, let the teacher do find all the numbers. And then I realized that I didn't know how to use the table. And it's a really easy table to use too, like once you know how to do it. So make sure you're getting the practice in. So if you look up in the table, this is going to be 0.5987 minus 0.0668, and that kind of makes sense, right? The 0.25, the area to the left of 0.25 should be pretty close to 50%, and the area to the left of negative 0.15 is pretty small. So overall, you get 53.53, and you can just leave it as a decimal if you want, 0.5319. So that tells us the chance, assuming the elephant weight is normally distributed with a bell curve with those parameters, the chance of observing an elephant in that interval is about 53%. Any questions on this question, on this one? All right.
Can I?
A question?
For like the greater than and less than signs, for I guess, does it matter or?
Yes, they're very important, right? Because which ones in particular are you talking about?
I was thinking like the P Z is less than negative 1.5.
That's right.
Because in like the thing it says it says Z, well, Z is greater than negative 1.5 on the left one. On the right one, it says Z is less than.
Exactly. That's a good question. So it's a lot about that's something to think about. I encourage you to think about why that is. But basically, you agree that this represents the in between the two numbers, right? Like Z is greater than something and less than something to the right.
Yeah.
This is in the middle. And this represents the area to the left. And this also represents the area to the left. But what we're doing here is we're taking the entire area to the left of the right interval, and we're taking away this amount. And when we take away this amount, it's related to keeping this amount, sort of. It basically, kind of, you can think of it because there's an interesting idea here. I really like that question. Like this formula is obvious from the picture, but how can you get it from just sort of basic rules? You have to think about intersection. So this is actually an overlap of two regions, and because you asked, I'll just kind of mention it here. So I'm going to say like this, so you can see where it's from. And again, you don't have to know this. If you're comfortable with the picture, you do have to do the right inequalities so that if it's consistent with what's happening in the picture. But probability that Z is greater than negative 1.5 and less than 0.25, this is equal to two things. This is a probability that Z is greater than 1.5, right? Intersected with Z is less than 0.25, right? So it's two intervals. Now, if you want to find the probability of two intervals, there's a neat way to do it. So here's one interval. That's the left one. Oh, sorry. That's not. That's the right one. And then that will be this one over here. And then over here, I'm going to just kind of do it over here. This would be the red one. So that will be over here. So to find the probability of the overlap, one way to do it that's kind of cool is we saw a formula to do this, right? The probability of the intersection is equal to the probability of both of them added. It's equal to this one, negative 1.5 less than z plus plus probability of z being less than 0.25 minus the union. Now, what is the union? Can anyone tell me what the union is? What is the probability? What kind of numbers are either greater than 1.5 or union? What kind of numbers are either greater than 1.25 or less than 0.25? Kind of a silly question. What type of numbers would be the union? What part of the number line would be the union of the green and red ray? Is it a specific part of the number line? If you look at the green and red ray, if you take their union, what do you get?
Can you repeat that?
If you take the union of the green and red ray, the union, so like all the dots that are included in that set, what is it? So you have over, it's going to be the entire number line.
Oh,
Do you see why? Infinity to infinity, exactly. It's everything. If you take the overlap, it's that middle part. But if you take the union, it's the whole thing. And so the probability of the union is just 1. So so now we can just change this to this formula. I'm going to rearrange it a little bit. Probability of z less than 0.25 minus 1, and I'm going to do something weird here. I'm going to write it like this. This is all a 1, but I'm going to add a minus sign because there's a plus sign here. I'm going to do 1 minus probability of negative 1.5 less than z. Okay. And then this turns out to be then, because it's 1 minus the probability of being less than, oh, hang on. Oh yeah, since it's probably one minus probability that z is greater than negative 1.5, this is actually probability of z being less than negative 1.5. So this is the formal way you can do it to justify that what we did earlier. But again, don't worry about this if you're a little bit confused. I think it's really neat to do it carefully from the principle that we saw about the thing we saw about the Venn diagrams, except in this case, the Venn diagrams are like infinite in size because they're infinite rays. So it's worth to think about, but really at the end of the day, it's as simple as, to find the area of the middle part, you take the big shape and subtract off the left tail. That's all. All right. Let's do one last question and then I'll let you guys go. I skipped one example, but it's a pretty easy one. So I want to buy a truck. I want to buy a truck. I'm out in the, was it, not the outback, I don't know what's in the savannah. I'm out in the savannah. I want to buy a truck or in the national park there, and I want to be able to, that would be able to tow 90% of elephants. What is the largest capacity, or what capacity should my truck be able to tow?
Do you mean like 90% of elephants, like all elephants, like 90% of them in the world, or just like there's a 90% chance you can tow that elephant, I guess?
Oh, very good question. So the answer is, I think, let me think about that. The same, right? So, and I'm keeping the same assumption that elephants are distributed with a bell curve of 13,000 and standard deviation 2,000, but I either want to take like 90%. I want to be able to tow 90% of the elephants, or in other words, if I pick a random elephant, there's a 90% chance that I can tow it. So what is the my question is, what is the minimum capacity? So I need to, my truck better be pretty strong to tow. So I need to find a minimum capacity, or what is the lowest rate capacity that my truck needs to be able to pull. Okay, so let's go with that bell curve again. So I know that I want to, here's the bell curve of all elephants, and I want to make sure, I want to find the threshold value that captures 90% of all elephants. So instead of writing 90%, I'm going to write 0.9. So let's figure out the z-score value that corresponds to that. So I'm going to go to my table, and can you guys tell me what number you find? What z-score value will capture 0.90 as a percent? And that's going to be inside of the table. So I'm looking for 0.90, and I'm going to find the z-score related to that.
0.8159.
Wait, Kai, what did you say?
0.8159.
How did you get? Not quite. So look up inside of the table. Try to find a number that's close to 0.9.
Oh wait. I just misunderstood. Yeah, sorry.
Oh, I see. Yeah, that's right. And that happens very often. We're going backwards now. You looked up the z-score 0.9, but now we want the probability of 0.9. Excellent. So I'm getting a few students here say 1.28, and I like that. 0.901. Yeah, I'm seeing 0.9015. That's probably the I don't know. 0.8997 is the closest one. Yeah. 0.9032. You know what, Diana, you can go a little bit, if you can get a little bit closer if you go to the one row above and start all the way at the right. It's actually a little bit closer to 0.9. So I find that the looking up for the z value that corresponds to the 98th percentile is 1.28. What that tells me, that number, is that if I pick a weight that's going to be 1.2 standard deviations above average, then that number, that weight, is considered to be the 90th percentile. And all it is to kind of find this weight is you can use that formula, but you kind of also feel comfortable with what we did earlier. So what is it? 1.28. In the notes, I do something different, but it's the same. I use some different numbers here. Equals x minus 13,000 all over 2,000. Or in other words, what you find, you can use an alternative formula. So just kind of solving this, 2,000 times 1.28 plus 13,000 is equal to x. The general formula, if you want to get the threshold value back from the percentile or the z-score, that if you have the z-score, you can do this. You can do mu plus what is it here? Sigma z. So it's the number of standard deviations plus the mean gives you the actual threshold value. And so what is that? 2000 times 1.28 is about 2.56, 2,560. So X would equal to 15,560. So I want to make sure to pick a car that can tow that amount, and this way I'll be sure that I can at least tow 90% of elephants. All right, guys, any questions on that one? How do you guys feel about this? Does it make sense? I'm going to post some. This will be the next test. Will be really heavily based on this. Yes, and it's really mostly on this stuff. So it's once you get the hang of it, it's actually really easy. It's a lot easier than the combinations and probability ideas, in my opinion. But I will be strict about using the correct notation. All right. Any questions at all? Just I will have some office hours if you need to do a retake. Yes. The correct notation. So just one comment, and I'll get back to Ace's question. The correct notation is kind of like where is it here? This. So a really good question. What am I looking for about notation? When I want to find the area, the probability of being in an interval, I want you to write this out carefully, and then once you look these up in the z-score table, replace these with probabilities. I've seen all sorts of weird stuff. I've seen people like put this number instead of the 0.25. I've seen people get confused with these numbers, and I understand it's like there's a lot of like decimals and stuff happening. So just make sure you're really clear and you're using probability of being between these two is equal to this number minus this number, and it's equal to this area minus this area, which is the final percentage. That's the type of stuff that I look for. Like being very precise about using the P and parentheses notation and stating it clearly. And then yes, the grade will just be the grade in the Google Classroom. I need to finish grading your homeworks, and some first tests I still haven't graded because I didn't get to meet with everyone. But I think I'll just probably look over them by now, and if I still feel like we need to meet, I'll let you know. But regardless, for the second test, if those of you who already heard me say this, you're welcome to go. I'm going to have office hours on Monday and Tuesday, and if you're welcome to stay after class if you want to discuss your second test. If you don't worry if you got a 0 or like something below a 6 if you failed. You can retake it, but you will have to do all the corrections. I really want you to learn how to do it, and I'm confident that you can. So yeah, please reach out to me, come by to office hours, rewatch some of the videos, and then let me know when you're ready to retake it. Just make sure it's like in the next 2-3 weeks, ideally in the next week and a half. Oh, office hours times. Yes. So Tuesday I'll have office hours 1 hour before class, so at 1 p.m. and then Monday it'll be at 1 p.m. Yes, everyone's test is graded currently. I think I have one makeup test that I haven't graded, but everyone's test has been returned. So I'll be around on Monday.
Have a great rest of your day.
All right, thanks, Archer. You too. Bye.
Thank you, Mr. Minsky. Have a great weekend.
You too. Bye, Olivia.
Goodbye.
See you. Bye, Ace. Okay, see you, Brandon.